So in this demo, we're going to go over repeated measures and how they work and how they're different than between subjects. So remember that between subjects means that each person is in a different level or condition. So what that means is that I cannot be in group 1 and group 2. Well, in a repeated measures design, I am in group 1 and group 2. And so the big distinction between the two types of experimental designs is that how many times a subject takes the IV. And so if they're only in one group of the IV, it's between subjects. If they're in multiple groups of the IV, it's repeated measures. And so sometimes people have a hard time differentiating in these sorts of designs between the independent variable and the dependent variable. Because we normally think about the dependent variable being the thing you measured and the independent variable being sort of the different groups that you're in. But in repeated measures, I'm in every group. So the way that I think about this is the independent variable is what the column name would be, and the dependent variable is what's in that column. So I've got the repeated measures data open here, and first off, it's sort of interesting because somehow it's decided that this first column is a string, right? Because it's left aligned. So I want to change that real quick to, oh no, it's considering it numeric. It's just left aligning for fun. Okay, just kidding. When you want to make sure that they're all numbers. But in here I've got heart rate measured over 3 different days. And what we did was ask them to do different things. So on day 1, we're getting their at-rest heart rate. On day 2, we're testing their heart rate after slow jogging. And on day 3, we're testing their heart rate after 30 minutes of cardio. So we would expect the heart rate to increase on these 3 different trials because we're asking them to do more hard work. And so it looks like it's just 3 dependent variable columns because it is. It's also 3 independent variable columns. So SPSS doesn't really make it nice and simple like with between subjects where you have a column that is IV and a column that is DV. Instead, you have all the columns are both IV and DV. So the way to think about it is that the IV is the title of the column. And so I have day 1, 2, 3, and what differentiates them is at-rest heart rate, slow jog heart rate, intense cardio heart rate. But it might be something like pre-post, or if you have people take questionnaires, clearly they're going to have a score for each question, that sort of thing. The DV is what the number is in the column. So think about that as like, what is this number? Well, it's heart rate. Then that's the DV. The IV in this one is what we did to make the heart rate change. Okay, so trying to keep those two things separate because that's probably the most confusing thing about repeated measures. These designs are more powerful, so you need less people in them to get the same amount of power. Let me kill iMessages here. Phone is... There we go. Okay, so I need less power. And what that means is if I've tested people multiple times, they're their own control group. And so this makes it really nice, because if you have crazy people in your data set, at least their crazy is controlled for. And so we're going to reduce the error variance. Remember, the error variance is the denominator, and so we want that to be small because that's within each group. And so if you have less error variance, you just have more power. That's the way it works. Because we're controlling for the fact that everybody is slightly different. The drawback to repeated measures design, though, is sometimes testing people multiple times creates its own problems, like they get bored, or they have what's called carryover effects, where if I take the same test 3 times, I'm going to get better just because I'm taking the same test over and over again. And so you kind of have to balance the effects of repeated testing with the fact that this gives you more power. Okay. So I'm going to walk through this whole example and do everything from G-power to mote, just like I did on the between subjects ANOVA. And so I'm always going to start with G-power. Let me get G-power here. Now, in G-power, I always have to change the test family to F because we're doing ANOVA tests, which are all F. And on a repeated measures design, that is going to be repeated measures within factors. I think the labeling on G-power is probably not the best, but what that means is that I have repeated measures only, basically. So I have repeated measures within factors, and so this should be repeated measures one-way designs. Okay. We're going to leave this thing as a priori, like we always do. And then let's hit determine, and you'll see that the window is just slightly different. So because I can't calculate this directly from means, because they're not different groups, but it still has our awesome direct partial eta option that we used in the last one. So I'm going to pick a nice medium effect size. If you're not sure and you haven't really found a whole lot of research on what your topic is, picking a medium effect size is a good place to start. Okay, so I'm going to calculate and transfer to main. So it gives me the same effect size as it did before. Alpha is always 0.05. And power, we've talked about a couple times now, is always 0.80. Which makes beta 0.2. Okay. And this is the confusing part. So number of groups is actually number of independent variables. And so this is how it's creating the sort of interaction effect, but we only have one. So we're going to put that as one group of people tested how many times. So number of measurements is the number of levels, or the number of times that they were tested, or in our data set, the number of columns. So we have 3. This new piece is called correlation among repeated measures. And this in itself is a measurement of power, because if your repeated measures pieces are not correlated, you're going to have a problem. Okay? Repeated measures will not work for you very well. The more correlated your columns are to a point, the better you're at. Okay? If you have no idea, pick 0.5. If you're working through data screening, you'll actually get this number, and we can estimate it a little better. And usually you would pick the lowest correlation. So if I have 3 levels, I would pick the one that had the smallest correlation to estimate here. But since I haven't really done anything, I haven't started, I'm going to start at 0.5. You can up that to 0.7. Don't ever make it 1 because it'll freak out. It might run, but it's going to be unhappy with you. So let's make that a nice, solid medium number. Okay. The last one is the non-sphericity correction. This is called epsilon in the output. And you're pretty much never going to have this number before you start. And so you don't really ever usually want to change it, but it'll help if you are halfway through a study and you're trying to figure out how many more people do I need. This is where epsilon might come into play. And I'll show you where epsilon is on the output and talk about it briefly. Okay. So I'm going to hit calculate. And it tells me I need 18 people. Think about this for a minute. We had 3 groups in the last study. The last between subjects one with the poor, fair, and excellent health. And I put in the same exact effect size, and it told us we needed like 120 people. So same effect size, same design, 1 IV, 3 levels, and look at the difference in the number of participants. Much less for repeated measures. And that's what gives them their power, is that we're controlling for differences a lot better. Okay. Now let's change that to 0.01. Let's see what happens if I make it a really small effect size. Okay, so the number of participants should go up. Okay, so it went to 161 people. Now you'll notice that denominator degrees of freedom doesn't match. Okay, so denominator degrees of freedom is calculated slightly differently in repeated measures. It's the same idea as group -1, group -1, group -1, but now we're testing groups multiple times, so it's not really people -1, it's number of scores -1. But it would tell us we only needed 161 people, but we would need 320 scores, that sort of thing. Okay. So G-power is very similar except for this bottom part. So number of groups is the number of IVs, number of measurements is the number of levels or conditions. And then I'm going to leave these bottom 2 alone usually as 0.5 and 1. So that's how to calculate power. So you will almost always see that you need less people for repeated measures design unless this correlation is very low, and then you're going to have a hard time finding what you're looking for. So from here, I'm going to run through the notes in the same order and talk about each piece of data screening, running the actual ANOVA, post hoc tests, moat, and pictures, because we haven't really totally covered how to do these graphs. So let's start with something we're familiar with. Let's go with assumptions. So I will do accuracy and missing data just so you can see it again, even though hopefully by now you've got the hang of it. So analyze, descriptives, and then frequencies. I'm going to screen all three of them. Move those over. Under statistics, let's get mean, min, and max, standard deviation, and what the heck, let's do skew and kurtosis. Under charts, I'm going to ask for histograms, and then hit continue. I'm going to turn off these frequency tables because they're going to be really big if I don't. So hit OK. Okay. There we go. Okay, so I have 18 scores in each day, and the means of the scores are going up, which is what I would have expected for this type of research. And then the variances are also going up, which makes sense too, because people are going to vary pretty wildly. And I think 20 points on a heart rate measure is not too unusual, right? If the average is 87, 20 points doesn't seem too big. Under skewness, look, none of them are skewed, none of them are kurtotic. They're actually pretty damn close to normal, which is good for us, even though we're not quite there to check that. And I would check my min and max to make sure they don't seem nuts. Now, 241 is going to be a really high heart rate, and so I might go back to the data set and make sure that it's actually written that way, and it wasn't supposed to be something more like 141. But let's assume that that's correct, because this is made-up data. But that sort of thing might be like too high. You want to check. And clearly anything 0 or negative in this data set would be incorrect. So I can look at for univariate normality if I wanted to right now, which is not quite the right order, but I could just look at my histograms and make sure there's nothing crazy. So look how pretty and normal they are because I used a normal distribution curve to make this data up. And so they are very normal. And so I would say that my accuracy is all right. If I then look at missing, there's no missing data. Cool, check, check. Now, we would want to look at outliers. So we're still going to check univariate outliers, although on the homework I think I just asked for multivariate. But let's get some more practice. So analyze, descriptives, and then descriptives. Okay. Move over all three of them. Save standardized values as variables to get the z-scores, and then hit OK. All right, I'm going to go back to the data. And since this data set's small, I can kind of look at it, or I could right-click on things and see that there's nothing too high or too low, although this one's close at 2.2. Let's go to day 2. Yeah, my computer doesn't always love to sort data sets. Okay, fine. So data, sort cases. Let's go day 2. All right. So nothing too crazy in this one. I don't even have anybody that crosses 2. And then data, one more time. Let's do day 3. And then I've just got somebody who's close to 2. So I don't have any univariate outliers on any particular points for any person. And then one thing I can do is now check for multivariate outliers. And so since I have multiple time measurements, I really would prefer that you guys do multivariate outliers. Why? Because somebody might have a score that is too high or too low univariate-wise, but overall is perfectly normal. Or they might have a pattern of scores that are fine univariate-wise, but multivariate-wise are just really crazy. And so this is the same reason we talked about for scales. It catches patterns of data that are weird and not just individual data points, which to me is much more useful. And plus, if the univariate and multivariate will also agree. So I'm going to delete this just to get it out of the way. All right, so to do my multivariate outliers, I need to first go to transform and then compute. We're going to make a random variable. So I'm going to, under function group, going to click on R so I can get there faster. And it's RV chi-square and 7. Okay, there we go. Hit OK. And then now I've got my random variable that I like to use. So let's run the fake regression to get all of the Mahalanobis distance numbers and the assumption checks. But if we delete anybody, we're going to have to rerun it, so don't forget that. Okay, these first couple times we don't tend to have outliers, but once you do, be sure you rerun the fake regression. Okay. So let's go to Analyze, Regression, and then Linear. Okay. My random variable goes in the dependence box. And then normally we talk here about like don't screen the IV, don't screen the categorical variables. Well, all three of these are the IV and the DV, so we want to screen all three of them. So when you're screening repeated measures, it's a little different than between subjects because instead of there being one dependent variable column, there's multiple columns that are both at the same time, so you screen everything. Okay, unless you've got a mixed design and then ignore the categorical ones. But we only have one variable and it's repeated, so we're going to screen just those. Under plots, do z-pred in y, z-residual in x, histogram and normal probability plots, then hit continue. Then under save, Mahalanobis. And continue, and okay. All right, so I'm going to need a chi-square table to tell what my cutoff score is. And so what do I use? Well, my degrees of freedom is 3 because I have 3 variables that I put into the independence box, and there are 3 levels. So I screen 3 columns, the dependent variable is 3. I'm sorry, the degrees of freedom is 3. So that makes my cutoff score 16.27. Okay, so remember, you're always using the number of columns that went into that independence box. So 16.27. So if I check out my Mahalanobis here, all right, and I sort descending, I clearly don't have anybody over 16.27. Okay, so I don't have any univariate outliers on any particular points, and I don't have any multivariate outliers, so look, they agreed. The only times that they won't necessarily agree is if somebody has like maybe 1 or 2 points, or they'll have maybe 1 point on a univariate outlier, but they won't be a multivariate outlier, and then every once in a while people will pop up that aren't individually univariate outliers and they'll become multivariate outliers. But what you'll usually notice is that their z-scores are in the 2s, so they're pushing it in the z-score area, but they'll pop up in the Mahalanobis set of scores. So no multivariate outliers. Cool. Now, we've checked for accuracy, missing data, and outliers. The fourth one is multicollinearity, and because we have multiple columns with dependent scores, I now need to check for multicollinearity again. All right, so let's go analyze, correlate, and then bivariate. I'm going to highlight the 3 dependent variables and move them over. So these are my 3 dependent measures. This are the 3 levels variables, but they all have the dv. So it's just 1 dv, but 3 times. And then hit OK. Let's check these out. Okay, so here's the thing. I need you to star this in your notes, make a big hoopla here, song and dance, happy faces, imagine me waving my arms around in class. And repeated measures, you expect them to be correlated. It's the same person over and over again, so of course they're going to be correlated. If they're not, you're doing something odd. And so it's the point. So in SPSS, you're going to get really high correlations. So normally we'd find this 0.1917 to be bad, because 0.9 is the normal cutoff for this, and 0.85 is pushing it, and 0.95 is really pushing it. So we will be like, oh no, we can't use these. The trick is, for repeated measures, it is actually good for them to be that correlated because it makes your design more powerful. So what you want to do is look for 999 or 1.0. that would be bad. Now, of course, these are here correlated at 1 because they're the same variable, day 1 and day 1. But you want to look here and make sure it's 999 or up. That's when they're too correlated, it won't run. If you have something that is that correlated, they are basically the exact same column, and you just need to pick one of them. So you would just drop one of them from your analysis. Okay, so we have some that are over 0.9, but this is special case. Repeated measures is a special instance where it is 0.999. And what I tell you to do to help keep yourself straight on all these different rules is maybe make yourself a chart of like, here's data screening for between subjects. So write out all the different things, like missing data, outliers, accuracy, multicollinearity, homogeneity, homoscedasticity, normality, and linearity. And then for each type of design, what we could do is look at like, yes, I check for this one. No, I don't. Yes, I check for this one, and it's special. So I'll try to help you make one of those charts and put it on Blackboard, and we can add to it as we go, because I think that'll really help clarify when I'm supposed to do what. Because the dummies guys are really good, the online notes, but it can get very tedious to find that particular one rule throughout the thing. I know this, okay? So we didn't delete anybody, and we don't have any multicollinearity problems, so I can just use the output I have. And for some reason, I really like starting with linearity, so I'm going to scroll up to my normal PP plot here. And I'd say it's okay. It's kind of different from the one I have in the notes, which has a little hump that is not good. But it's mostly close. Right here is really the problem, where it's below the line here and above the line here. So you might say that it's bad up here at the top. Okay, it's getting close. And what I could do to figure out maybe who's the problem, and this is not in the notes, is look at those bivariate scatter plots or that matrix, scatter matrix that we did. So I told you how to do this in Chart Builder, but after talking to a bunch of you this week, if you go under legacy dialogues, this actually works a little better, which is kind of ironic. So graphs, legacy dialogues, this is the exact same thing as doing it the other way. Go to scatter dot, and then it's matrix scatter. Hit define. And then just put these variables, first 3 variables here. Okay. So they've moved to Chart Builder, which gives you a better picture of what the heck you're about to get. So this is not the pretty version, but it seems to work better. So let's try that. So it gives me my 3 little graphs, and none of those are curvilinear. I mean, they're all pretty straight. And so, yes, it looks a little bad here. I would say that this area is maybe not so hot. But if I looked at each pairwise combination, they're really very linear. So I'm okay. So that's an example of a time when if you aren't sure about the multivariate version, you can look at the univariate version and go, yeah, sure, whatever. All right, next I've got normality. So this box. Now I do have a bar that's quite taller than I would expect out here. It does run from 1.5 to 1.5, which is pretty normal. This doesn't look like my box at all on the notes, so kind of an amusing side note that sometimes you don't get the same things twice. And so this might be problematic that it's so tall over here. So if I wanted to check out who was the problem, I could run that frequencies analysis we did a minute ago. So I already have it, so I'm going to scroll back up. And so here's day 3. It's pretty normal. It's a little like maybe kurtotic because it's only got, the spread isn't so great. And here's day 2. It's pretty normal. Day 1's really normal. So while my multivariate chart does seem to have maybe a touch of a problem, the rest of them are all normal. So again, I'm okay. And we looked at skew and kurtosis at the beginning, and since I haven't changed anything, those numbers haven't changed. And so I don't seem to have any problems. All right. Last one we're going to do is homogeneity. So I'm going to double click on this and get that line of best fit because that'll just give me the 0 line and I can kind of see everything that's going on a little better. You don't have to do that for your homework. I just think it helps a little bit to see what's happening. Okay, now over here we are starting to see a problem, right? Because it goes to a little past 1 and this one goes up to 2. So the spread is not actually that even around 0. So that might give us a little bit of trouble. They are pretty evenly distributed, like there's enough at the bottom and enough at the top, but this, especially this bad boy over here, is sort of pulling us pulling out homogeneity. Okay. Now to look the other way, I've got 1.5 to 1.5. That's perfectly good. At 0, they're pretty evenly split. So we might start to see some little problems here because they're not evenly spread around 0. Okay. Now, here's the new one. So this is at the end of the notes right before running this analysis. Is sporicity. Okay. And I don't know the best way to describe sporicity. So sporicity is sometimes called compound symmetry. And what it is this idea that there are the correlations between each of the levels or each of the time points is the same. That's pretty easy. So instead of the variances being the same, which is homogeneity, we're looking for the correlations between time points to be the same. Because you would assume that people are going to stay pretty consistent if you're testing them multiple times. But also we want the variances between the different scores to be the same. And that one's weird. So it's like time 1 minus time 2, take that score, and then time 1 minus time 3, take that set of scores, time 2 minus time 3, take those sets of scores, and see if the variances are all the same of those scores. Okay. That is almost impossible to meet. And I'll try to draw you a little picture here. I'll do this in PowerPoint. My drawing on my laptop is insanely bad, so just bear with me. Come on. All right. So let's say we are doing a weight loss test. Okay. So here is time 1, here is time 2, here is time 3. Okay. So at time 1, I have participants who average here. So we're taking participants who are overweight and we're trying to get them to lose weight. And so here's the 95% confidence interval, or what those error bars happen to be. So we got a pretty good spread of data. Okay. At time 2, people are losing weight. Yeah. So they're going to come down. And then the spread of the data is going to come down because that's just the way it works. Because as people's scores come closer to the bottom, their scores cannot vary that much. And then time 3, we're going to kind of level off. People are plateauing, but the variance is going to get very small. Okay. This would not meet the assumption of sporicity. Okay. Sporicity is that the correlations stay the same, which they probably would, but that the variance, or the spread here and here and here, is the same. And so if we're trying to find the differences between these levels, we're almost expecting the variance to not be the same. So if you think about, like, I'm trying to get people to stop smoking, or I'm trying to get people to lose weight, or in this example, we're trying to see what the heart rate does, and so the variance is going to get bigger because people are going to have bigger differences in their heart rate. I don't expect those to be the same. And so sporicity, in my opinion, is kind of a stupid assumption because you're assuming something that is naturally not going to happen because of your research study. So if you want people to change in some way between the 2 time points or the 3 time points, the variance is going to move around, or maybe your study is not effective. Now, that's not always true. Sometimes it works out, but generally the way we design these studies sort of forces that assumption to not happen. And so a lot of people will ignore sporicity. I'm going to show you where it is on the output and how it works so that if someone asks you about it, you know what it is. But generally, I'm like, whatever, move on. Okay. And so homogeneity and sporicity go hand in hand. So homogeneity is equal variances for between subjects designs often, and then sporicity is equal variances for repeated measures. It's not quite that simple, but that's a good way to keep it straight, which one's which. And so what we'll do is we'll ask for homogeneity, but you'll see that SPSS will kind of balk at you and be like, what are you doing? So here, if it doesn't totally meet the assumption, it's usually okay, because sporicity is going to be tested again later, and then that's, like I was just saying, kind of problematic in its own self. So if this one's not perfect, we'll kind of bend the rules. Okay, so all that being said, it looks like I meet most of the assumptions with maybe a little bit of trouble with homogeneity, which we'll test for sporicity here in a second. So let's actually run the analysis. So I'm going to go to Analyze. Still under general linear model because this is still ANOVA. And I'm going to go down to repeated measures. Okay. And this is new. Okay, so this window is basically asking you how many variables do you have and how many levels do each of those variables have. So we're going to call it something other than factor 1. So why does this happen? Well, this happens because SPSS knows that when you're doing repeated measures, there's multiple columns from the same person. And so it's finding a way to combine that into one thing. So it's kind of creating a separate variable that's like, okay, here's the IV. Now all of these are the DV. So it's just because of the way they've set it up. Okay, so I am going to call this days, or we can call it different heart rate tests, but I think I call it days in the notes. Okay. And it's got 3 levels. So I want to enter a 3 here and hit add. Okay. And you will see that as you add variables here, that will change what happens in the next window. Okay, so let's hit define. And since we picked 3 variables here, we've got 1, 2, 3 little spots. Okay. Now, it is very important here that if the spots are ordered in any particular way, so in our way they are because we have different days that we're testing different things, or if you're time 1, time 2, time 3, you need to put them in the right order. Okay, so SPSS does kind of assume that they're in a specific order. Now, if they're not, like if they're like test, if they're just 3 different types of exams, then it doesn't matter what order you put them in, but generally if it's got an order, make sure it's in order here. Okay. And then from here, so I moved all 3 of them at once. I'm going to hit options. Okay. This is the same window you've seen before, so I'm going to move days over here. Right? And then there is descriptives, effect size, and look, homogeneity flipped. It was above transformation matrix because nobody can keep the windows consistent across tests, so I'm going to pick homogeneity. Okay, normally you wouldn't need it. It's going to tell me that I'm stupid for doing this. But this is what I was talking about like last week, where I want to be able to remember to click all the right things once you get in the habit of doing these things. And if you click those 3, those are the big 3, and as long as you're doing an ANOVA, if it just tells me I made a mistake, and whatever, I don't care. Okay. We're actually going to do something else in this window, but I'm going to show you something else, show you why first. So I'm going to hit continue. Now, clearly we want to do a post-hoc test because if our test turns out significant, I want to know where. So how are the days different from each other? But if you click on post-hoc, you get this because SPSS is dumb. So no one has ever taken the time or trouble to program repeated measures post-hocs in a way that makes any sense to anybody, and so it actually is blank. So post-hocs will only pop up if you have between subjects designs, which we don't. So I'm going to hit continue. But here under options, you see this compare main effects piece. This is actually a hidden post-hoc window. Okay, so I'm going to pull that down. So I've got 3 options. LSD, which is none, so it's a least significant difference test. It's just dependent T, no correction. I've got Bonferroni, which is a dependent T, because this is repeated measures, with a Bonferroni correction. And then I've got SIDOC, which is actually a SIDOC-Bonferroni correction. And so the way those 2 work, since I haven't totally explained them to you guys yet, is that, so we got Bonferroni. Okay. So we have alpha, right? Alpha is our type 1 error rate, and we usually set it at 0.05. This is why we're looking for P less than 0.05. And the way Bonferroni works is I'm going to take the number of comparisons. So I'm actually going to go ahead and make that table. Group 2, P. There we go. That we made before. So group 1, group 2, P. So this is sig. I'll explain what it means, and then D. Word makes me crazy about that. But anyway, so I have 3 levels. So it's going to be day 1 versus day 2. Day 1 versus day 3, and then day 2 versus day 3. So this is the exact same setup I did earlier, where I put in every group versus every other group. So when you have 3 groups, it's always 3 comparisons. Okay. And so I've come up with the fact that I have 3 comparisons. Okay. And we'll use this table again here in a minute. Okay. So I got 0.0, the way that Bonferroni works is that it is alpha divided by comparisons, which in this case is 0.05 divided by 3, 0.0167. Okay. And so essentially what we've done is we have said, well, we're going to correct this, and we're going to make alpha our p less than number 0.0167. That's kind of a pain to look up. So we're just going to ask SPSS to do the correction for us. So it will correct on sig, and we'll keep looking for 0.05. I think it helps a little bit to know what Bonferroni is doing. It's actually the simplest one to run without, if you don't have any particular program and you just have dependent t, you can just kind of do it in your head. Whereas Tukey is a little bit more complex. It's full of tables that you don't want to know about. But they all fixed sig in the output. So you can keep looking for 0.05, so you're not confused about what's the new cutoff score. But I think it's interesting. I think it's important to tell you a little bit about Bonferroni. The way that SIDOC works is it is 1 minus 1 minus alpha to the, so my little character here, caret, 1 over c. And that works out to be very similar to Bonferroni. And so the good thing about computers is they can do this to lots and lots of decimals where it will actually be useful. So we got 1 minus 0.05 to the 1/3, which is 1/3, okay, which works out to be 0.95 to the 1/3, which today is 0.9832. So if I did 1 minus 0.9832, so I did this on my calculator. So 1 minus 0.9832, and you will notice that that is approximately 0.0167. Okay. Now, the decimals out past that point are different. But often people will say they're sort of interchangeable. Not quite. I like SIDOC better because it's a little less restrictive. But when I mean a little less restrictive, it's like your conservative mother versus your conservative grandmother. It's very close. So you can pick either one. I'm cool with both. So let's go back to the data set here. And I'm going to switch this to Bonferroni, I think is what I did in the notes. So I'm going to be consistent for once. And do the same thing. Okay, actually, I don't think I talked about this in the notes at all because I made these before I realized what this window is doing. So add this to the notes right here where you are clicking compare main effects and adding in Bonferroni because this will make your life so much easier. Okay. All right, so hit continue and okay. So the very first thing that happens is it gives me a warning. No homogeneity. Okay, so, okay, great. Later, I don't care. Okay. Now, it tells me what my within subjects factors were that I entered, so this is just a summary of what you put in the independence box. Here are my descriptive statistics where I got my mean and standard deviation and n, so that's going to be really super helpful for our Word document I had going for looking at moat later. Right. And then it gives me this multivariate window. Ignore this. It doesn't exist. You don't see it. We are not doing profile analysis. So ignore the multivariate window. In fact, so much so that I'm going to hit delete. No, my computer is not going to delete. Pretend I deleted it. All right, let's go down. So the next box you're going to get is sporicity. Okay. And so I'm going to look here at sig. So eyes directly go to it. And you want that to be greater than 0.001. Remember, this is data screening, new kids on the block, no 000. So no 000, that would be bad and you would have to do something. So I am scraping by. I am just barely making it, but I'm good. If I wasn't good, what would I do? So if someone asks you to do a sporicity correction, what do you do? And this is where epsilon comes in. So when I was talking about G power and it said non-sporicity correction that said epsilon next to it, this is the number they're talking about here. And so greenhouse geyser, this first column, is the most popular and the most common. Okay? If both the greenhouse geyser and the Hunfeld here are are less than 0.75, you want to use greenhouse geyser. Okay, so if both of these bad boys are less than 0.75, use this one. Okay, and I'll show you how to use it here in a second. Because right now it's kind of like, okay, so what does that mean? If they are over 0.75, use Hunfeld. Don't do lower bound unless you just like absolutely are forced to, because it is really restrictive. Okay, so these are corrections for sporicity problems, and so the rule is kind of at 0.75. Well, I would find, so I don't need to do anything, but if you do need to do something, it's going to be in this box. Okay, so the next one you would look at is, here's my ANOVA box. This is where all the action is happening. And you will see that is very different from the ANOVA for between subjects, like radically different. Okay, because again, no one can program multiple windows. They all did different ones. And so what happens is if the numbers up here get translated down here, so this correction is applied to degrees of freedom. So if you took your degrees of freedom 2 and multiplied it by 0.643, you would get 1.29. So what's happening is here, it's multiplying your degrees of freedom times the correction number, the epsilon number, and that's where these weird partial degrees of freedom are coming in. And I said a lot of people don't do these corrections because it's sort of a catch-22 with your design, but here's the other reason why people don't do these correction is they don't understand that these things are real. So I've submitted papers where we did do the correction because it was like really bad and we needed to, just to kind of cover our asses. And I had a reviewer write back and tell me that I had done something wrong because I shouldn't have gotten degrees of freedom with decimals. And so I had to find a polite way to say, actually, no, you're wrong because they actually are decimals. And so in the end, we had to just take the correction out because they didn't know any better. So a lot of times this happens just because people aren't familiar, even though it's right here in the output. But generally, we're going to stick with sporicity assumed, unless you just really need to correct. And so what's going on in this box? So if I'm picking sporicity assumed, I want to stick with it all the way across for both my IV, where days is here, and my error part, the between subjects part. So let me pull up Word again. Oop. I swear, thing is possessed sometimes. There we go. So if I wanted to write out, did the overall test work? Okay. So is my omnibus test significant? Okay, because that's the first step. The way this works is it's still degrees of freedom between, even though it's a repeated measures design, still degrees of freedom between. And then degrees of freedom within, okay, equals my F value. P equals my sig column. And then eta squared is still partial eta. Okay. So what I would do is write F, and then I would use the degrees of freedom under my IV, so 2 here. And then the degrees of freedom under error, so 34. So it's levels minus 1, and then it's scores minus 1 plus scores minus 1 plus scores minus 1, or something very close to that. That's actually not quite what it is, but it's really close, so we're going to pretend, because that just makes sense. Okay. And then I have my F value, which is really huge, 633.46. I'm going to put in P. Now, don't do this. No, bad, wrong. Stop. Okay. If you get 0, 0, 0, do less than 001. Because it's less than 001, because it only shows you 3 decimals. You can actually double click on it and get more decimals, but this is good enough for me. So less than 001. Okay, thanks Blackboard for letting me know. And then I'm going to do eta squared is 0.97. Generally, if I ever got this in real data and I knew it wasn't made up data, I would freak out at this point, because 0.97 means 97% of the variance is accounted for by the IV, and that is out of control. That is like not true with people, right? We can't usually account for 97% of their variance. That's just nuts. But I made this data up, so I know that it's going to be high, so you won't see scores that high normally. And if you do, you just want to make sure that you haven't done something weird, because that would generally be a crazy effect size. Okay. All right, but this is how you would write it up. So we figured out that our omnibus test is significant. Huzzah! So now I need to figure out where. So what happened? We know something happened. Now tell me where. Okay. So we'll go back to my output here. And in the theme of too many boxes and not enough things that are useful, you're going to get this within subjects contrast box. Don't use that either. Oh, look, here are the notes where I told you how to add the post hoc test. Yay, it's in there. Okay, I think I misspelled Bonferroni though. Oh, no, maybe I've been misspelling it this whole time. So pretend like you didn't see that I butchered Bonferroni's name, and that it's 2 R's and 1 N. All right. And that will be forever immortalized because I won't re-record the video. Anyways, back on track. For within the subject's contrast here, this is if you really wanted to know if it were a linear effect. So are we going up or down over time? But if you're going to do that, just run a regression. So we're not going to do that. So we're going to ignore this within subjects box. Now here's the thing. People get really confused because suddenly there's a between subjects box here in the middle of nowhere. And that is the one for the last ANOVAs that we did. You don't want to use that either. Now the good news is it doesn't show you anything. Like this is intercept and error, but it's got enough numbers that it sort of looks like it might be the right thing. So I'm going to just warn you, do not use this box on repeated measures designs. And when I ask you to input the ANOVA box into your homework, don't give me this one because I would count it wrong. Okay, so be sure that you're looking at just within subjects effects because that's what we're doing is repeated measures and ignoring between subjects effects. If we're doing a mixed design, you will need to look at this, but we're going to get back to those here in a little bit. Okay. So I figured out that something happened, and then here in the notes I talk about how to get dependent t with the corrections, and I talk about Bonferroni, but I talked about that in the video. And so I am going to scroll down until I get to this pairwise comparisons box. And this is where all the Bonferroni stuff happened. The other thing I showed you how to do in the notes is if we didn't want to run it using this Posthoc method. Okay, the Posthoc method is a little bit easier where you ask it to do compare main effects and then pick Bonferroni. But I'd like you to see what the dependent t option looks like because you're going to need it in one of the next sections. Okay, so I'm going to go in the order of the notes here. So let's do analyze, descriptives, just kidding, compare means, and then paired samples, okay, because this is dependent t. I know that's been a while, but it's dependent t. And so this is where I would put them all in. So I would do 1 versus 2, 1 versus 3, and I'm holding down the control button, or if you're on a Mac, the command Apple button, to pick specific ones. And then 2 versus 3. Which is the exact same box I made over here in Office. Okay, so 1 versus 2, 1 versus 3, 2 versus 3. Then I hit OK. And so that will give me the paired samples test or dependent t, and this would be no correction. Okay, this would be if I wanted to do it, but I didn't care about type 1 error, like, oh, screw that thing that she was telling us about, and I didn't want to correct at all. So this would be, I could report this just like you did in the section for basic statistics with T, degrees of freedom, P, and Cohen's D. But what I'm going to do instead is actually do the correction and go up here to pairwise comparisons. Okay, so you can do this either way. I'm going to recommend doing the correction because why would we do it in one test between subjects and not do it in the other test for repeated measures? That's like cheating. So let's make this chart down here. And so I did it in the notes by looking at just the dependent t box, and then I would say they were all significant, but then I would have to apply that correction and like do the math by hand, which I showed you is not hard. I would have to do all of this, and then I would look at those p-values. But I'm going to go with the way that's much easier because I am as lazy as you guys are when it comes to getting things done in an efficient manner. And so I'm going to look at this one instead. Okay, so 1 versus 2 is 0.000. So I'm going to write that here as less than 0.001. Okay. And they're actually all less than 0.001. Hey, where's my output? There it is. So right, see, you see all less than 0.001. Again, it gives it to you in both directions because it thinks you're dumb. And so I am going to just look at 1 versus 2, 1 versus 3, and 2 versus 3. Okay, but they are actually all significant. Okay, significant. There are differences. Okay. Now, what are those differences? Well, I would type in my means again. So A 7.5. SD is 16.73 for day 1. And I'm not entering in. Why am I not entering in? Because they're all the same. So I don't want to repeat myself. So on day 2, I got 134.11. Oops. And 21.75. So enter that for day 2. And then here it's 189.56. And standard deviation is 27.75. Copy, copy. All right. So here I said it was significant. Now, how is it significant? Well, between day 1 and day 2, the difference there is at-rest heart rate versus slow jog. So my slow jog group has a higher heart rate than my at-rest. Not surprising. And then it's at-rest versus intense cardio. My intense cardio has a higher heart rate than at-rest as well. Good. That's what we would expect in life. You know, if I'm comparing my slow jog to my intense heart rate, it seems that my intense cardio has a higher heart rate than the slow jog. So get out there and do intense work for high heart rates. Now, so that gives me the what happened in each piece. And so that's where I could write up a lot of this stuff. But instead, I want to also include how strong that effect is. So remember, the point of effect size is to look at the strength of the relationship. So exactly how big is the difference between groups. Okay, so I'm going to pull up Moat. And on this one, remember you have 2 options. So we've got dependent T averages, dependent T difference. Okay, either one is correct. If you go this Bonferroni route, where you have this little table, right? What you're essentially going to probably want to do is do dependent T averages. Okay, so that was the first one I went to. Because you have the means and standard deviations, because I just wrote them all down here. And so I could type them in one at a time like we did before. Okay, so let me do that. So A 7.5. I'll tell you why not the other one here in a second. 134.11. Okay, so it calculates that mean difference, which you'll notice if you look at the output is this number here. So 4661. I could just enter that number if I wanted to. Let's go back to here. Right? So my time 1 standard deviation, 1673. Time 2, 2175. My size value is going to be 18. So you see there's only 1 because there's only 1 set of people. The T statistic will not match the SPSS output, but my Cohen's D is 2.42. So it's a very big effect size because I made this data up. Okay, let's do day 1 versus day 2. So 189.56. And then 27.75. So 4.59. So if you get a big eta squared, you should also get very large Cohen's D's. Okay. Not all of them will be large, but most of them. Okay. And then, oops, got excited here. I've got 134.11 versus 189.56. 21.5. The rest should be the same. And I got 2.24. So the biggest difference is between your at-rest heart rate and your intense cardio, which makes sense. Okay. So I'm going to list this as D average. When you write this out, the lowercase d, Microsoft Office, you can just do it like this, or if you want to do the super fancy subscript, that would be the best way to do it. Okay. So why D averages and not D diff? Because I actually told you at the beginning of the semester that I like D diff better. All right. If I go down to D diff, I can enter time 1 and time 2, but then it wants the standard deviation of the differences or the standard error of the differences, right? And so you don't really get that anywhere. Okay, you might be able to use this standard error number. So let's see if that works. Oh, okay, well, JK, you can do either one fairly easily. You used to not be able to do this quite so easy, where now I can enter mean difference and standard error from this box. So it might actually be a little easier because you don't have to type so many numbers. But either way, so I could enter the mean difference, 4661, and then be sure you enter this under standard error. So see here, it's a standard error. Make sure it's under standard error down here and not standard deviation, or you will get numbers that are totally nuts. 185. And then I have to enter in here, so I got 18. Okay. And so that will actually match the T results. So let's check and see. So it gives me a T of 21. Here's my T of 21 right here. And then that's Cohen's D for the first one. It's 5.03. Check out the difference. So if I did D diff, here, let me just add a new column here. 5.03. So check out how different they are. Let's do a couple more, just to kind of make this point. All right, where was I at? I was looking at this box, right? So I got 102.06, and then my standard error of the difference is 3.79. Okay, still 18 people. My Cohen's D is now 6.35. And then a lot of window flipping, but now the last difference is 55.44. And my standard error of the difference is 2.36. And so my D value is 5.54. Right? 5.54. And so you will get very different numbers. So if you do this one, your friend does the other one, don't expect to get the same numbers. And the T values will not match if you do D averages. Okay? But you can calculate them from any of the pieces of information you have. It's just for D diff, you really need to make sure you're using the difference scores. And so if you have two numbers here, you can't do D diff. Okay, you can't subtract these two. Don't do that. That's bad. Well, you will get radically different numbers. Now, I like D diff because I always find it a little easier if I'm working from dependent T. But the argument is that D average is more appropriate because it's not quite so biased. It's a little lower usually. Now, these are super huge numbers already. But that's how you can get effect size, either type of effect size using mode. All right, so the very last thing I'm going to cover is how to make this chart. Now, we have not done this chart yet. So it's going to be a new one, and I'm going to show you two different ways to do it. I only have one way in the notes, but I'll kind of show you two different options, and both are correct. So let me close mode here, and then get to the data. So let's go graphs and chart builder. Now, since this is mildly continuous on the bottom, we could actually do this as a line graph because it is a sort of, we've done day 1, day 2, day 3. Okay, so I would pick line graph and pull it over. Now, here's the fun part. You want to take all 3 variables at once. Okay, so highlight all of them and then drag and drop that into Y. So you get the red cross plus. Okay, I'm putting all 3 into Y. Don't put anything into X. That's the tricky part. Okay, that's what we haven't really done so far. Because I'm saying that all 3 of these are the dependent variable. So then you'll get this create summary group thing where it creates a X variable for you. So it sort of creates you a special dummy variable that is, okay, so there's an X variable in here somewhere and it's like each column is a separate level. So I'm gonna hit OK. And so you see it gave me an index out here. All right, that means that it's a fake variable because look, it's got the little star next to it. Okay, so I'm gonna hit display error bars. And then I can, be sure you hit apply. I could clean up everything here. So my one of the big problems is it won't show you that x-axis label because it made up the variable. So I could put in here exercise type for x. And then here under y, it's just going to list mean. So these are the stupidest charts because you spend the most time cleaning them up. Let's say it's average heart rate. All right, and I'm going to force the minimum to be, let's let it do automatic. I could make it 0, but then you would be dead. So let's just leave it as automatic. So hit apply, and then okay, wait, where are my error bars? Let's see if it stuck. Ah, it didn't stick. There we go. Apply. All right, so this should be very similar to the one I have in the notes. Look how nice and pretty and linear it is. I forgot to hit apply for my y variable, so I can double click on that and then change it here. So click once, click again to get where you can fix it. So average heart rate. Okay. And then here I might, instead of labeling them as day 1, day 2, day 3, I might do at rest. And then, what was the second one? Slow jog. And then the last one, intense. Okay. Now a line graph is appropriate because I have data that is sort of, I've tested it in a linear, a continuous sort of way. But if you didn't want to do a line graph because maybe you have like 3 different forms of the same test and there's no good reason why it should be continuous, you can make it a bar graph too. Okay, so graphs, and then chart builder. Instead of line graph here, I'm going to switch to bar. So let me hit reset, just clear the screen here. I'm going to move my bar graph, my single bar graph over, and then it's actually the same set of steps. So I take all 3 of my repeated measures pieces and dump them into Y. It's going to do that same indexing thing for me. And then I would go through and kind of clean everything up. Display error bars, change all the X and Y labels. I won't bore you with it this time. And so I could have this sort of graph too, but be sure you change all this stuff. So you see here, because I didn't ask for an X-axis label, there's nothing there. You need something there. Okay, the bars need a label and the X-axis needs a label or you will get half of it wrong. Okay, so if that happens to you, double click to activate. Here under X, you can go to, I think it's labels and ticks, display axis title. Okay, let me cancel and do that again just a little bit slower because I was making sure I remembered what it was. Okay, so hit X over here for select the X-axis. And then I think it picks categories. So if it's on categories, click labels and ticks and then display axis title. That will give you, apply, something to work with out here because you can't just randomly type here. So, and then I could say exercise type. Okay. So that's how you can add an X label, or if you accidentally delete the Y label, you can get it back. So the tricky part about graphs and repeated measures is really that dumping all 3 of them into Y. Okay. Now, if you're going to write this up, if you look at the way that I have written it up in the output on your notes, I have the t values. So the way I did this originally, I went in and did dependent t and then talked about the, I would have talked about the Bonferroni correction. And so if you're not going to do that, what I would tell you to do is if you're going to do the easier version and use the SPSS to create the Posthoc scores for you, I'd actually tell you to go back and do it just like the between subjects output, where you have, so if I was reporting this, I would say slow jog, heart rates are are significantly higher than at rest. And then I would just do P, oops, D, and then I'd pick. If I did D diff, okay. And so I would just do P and D diff, which is very similar to the way that between subjects is run. But when you're typing it up, you're going to say, you know, the ANOVA was significant, stuff, but then dependent T tests with a Bonferroni, spelled correctly this time, correction, were used to analyze post hoc differences or something. Okay, so you would have a line about what type of post hoc test you did and what type of correction that you used. And so they know where the hell these p-values came from. Okay, so it was a dependent T with Bonferroni. If you say that you did that, suddenly it makes sense why you don't have t-values. Okay. Or you can do it just like mine. In the notes, I think it's probably shorter to do it the way I'm talking about here, because you don't have to add in all those extra t values and stuff. The other thing I did was I added the mean difference scores. That's because I was reporting t. You can do it just like I have it here written out, because if you have a chart, you don't really need means and standard deviations in the write-up. And by chart, I mean picture. So if I have a picture of the data, I don't always really need means and standard deviations in the text as well. You can do both for me if you want, because I don't mind. But often people will say that's too repetitive to have them both in a picture and in the text. And then the further we go, the less we'll actually use means and standard deviations in text, because you'll have a lot of numbers, and so you'll really want to make a chart, a table, or a figure for that. And that is the end of repeated measures, and so the next section will be over factorial designs where we have multiple variables.